Hey, today I thought I would do something a little bit different, and what I want to do is take kind of a deep dive into the beta function. And on the board here, I think we have the most well-known form of the beta function. We have this integral from 0 to 1, t to z1 minus 1 times 1 minus t z2 minus 1 dt. And the reason this is so useful is we can express our answer in terms of the gamma function over here on the right, and this tends to be pretty easy to calculate depending on the values. And I've done a bunch of other videos on this, and I have a playlist. So if you need some more of the background on this, I'll provide a link to the playlist. But in this video, what I wanted to focus on was some other forms of the beta function. What I did over here on the right is put down 4 different integrals that are all different forms of the beta function. And you'll notice the first formula, the first integral is just what we have up here on the board already. And so we have 3 alternate forms. And of course, there's other forms floating around out there. I just wanted to focus on these 3 right now. And what I want to do is take a look at these last 3 integrals, 2, 3, and 4. And I just want to show how these are the same thing as our first integral. All 4 of these integrals are equal, and they all give us this formula in terms of the gamma function. And so we could use any of these and go straight to our answer in form of the gamma function. So where I wanted to start was just with this second integral from the board, noticing that I think this is the most similar to our first form, so it shouldn't be too hard to go from here to here. You'll notice one important difference is just this n exponent here. If you didn't have that n exponent, you'd just be very close to being able to use this form. So what I'm going to do is I want to handle that. So I'm going to make my u substitution. I'm going to say u equals t to the n. And then du is going to be n t n minus 1 dt. And then let's just solve for dt real quick by dividing by this business on both sides. So we're going to end up with du over n t n minus 1. And then let's see what happens when we make this substitution. So first we'll plug a 1 in here. If t is 1, no matter what we raise to, it's still going to be 1 here. And if we put a 0 in here for t, we still get 0. And then I'm going to leave this first term for now, even though we're in u. We'll just kind of leave this here for now, and we'll handle that in a second. So then we're going to have, this is going to be 1 minus u to the same power. And then our dt is going to be this, du over n t n minus 1. Well, the n's are going to cancel here. And then let's just deal with these t terms. So we're going to have tn z1 minus 1 over tn minus 1. Well, using exponent properties, we can just turn this into one expression. So we're going to have nz1 minus 1 minus n plus 1. Well, the 1's are going to cancel. Then because we have n here and here, we could factor an n out, and we could write this as n z1 minus 1. But then by exponent properties again, we could write it like this. But t to the n is u, so when we rewrite this, we have the integral from 0 to 1. Our t's become u to the z1 minus 1. Then we'll have 1 minus u zt minus 1 du. But notice this thing is exactly the same as our original beta function right here. It's a different variable, but the variable name doesn't matter in a definite integral. So we've shown that our second integral is the same as our first integral. Okay, so we've handled the second integral. So now let's move on to number 3 here. Okay, so for our third integral, this one's really nice because it allows us to use the beta function when we have an integral with trig functions. And what I want to do here is I just want to reorganize this a little bit before I do any kind of substitution. I'm going to want to set up a substitution, but what I'll do is I'll strip out a cosine here. So we'll write this as cosine t dt, trying to set up a u substitution where my u is going to be sine of t. So if I strip out the cosine to change this exponent here, so this is going to be 2 z2 minus 2. But then I could factor a 2 out of this and bring it on the cosine. So we can just rewrite this, factoring the 2 out, we can write this as z2 minus 1 here. Let me put my sine term back. But then one more thing before I do the substitution, let's rewrite cosine squared. Let's write this as 1 minus sine squared t. So then when I make my u substitution, we'll have everything in terms of sine and just this one cosine over here. Okay, so now we'll just do a very simple u substitution. My u value is going to be sine of t, and our du is going to be cosine t dt, which we have right here. So when we do this, we'll have our 2 out front still. If I take pi over 2 and plug it in, sine of pi over 2 is 1. If I take 0, sine of 0 is going to be 0. Then sine t is going to be u, so we're going to have u 2z1 minus 1. I hate writing z's. So here we have u 2z1 minus 1. Here we're going to have 1 minus u squared z2 minus 1. And this is just going to be du. And then at this point, this is starting to look pretty familiar. Let's go back to our formulas. What I want to notice is this integral here is actually in the form of number 2. Notice we have a 2 here, we have a 2 here, and we have a 2 here. So we can say if you set n equal to 2 and you go to this equation number 2 right here, you have the 2 in front of the integral, you have the 2 on the z1, and you have the 2 in the exponent here. So just knowing that integral 2 here is the same as integral 1, we can rewrite this as the integral going from 0 to 1 of u z1 minus 1, 1 minus u z2 minus 1 du. All I did here is exclude all the n terms, and this is just all from what we did on the previous board. And so, of course, this is the same as our equation 1 up here. Okay, last and maybe the most interesting is this integral number 4. We have this integral going from 0 to infinity, t to z1 minus 1 over 1 plus t z1 plus z2 dt. And for this one, I'm going to go right to a substitution. I'm going to call my t value equal to tan squared of u. I'll take my derivative. So our dt value, first we'll use the power rule, so this is going to be 2 tan u, and then the chain rule is going to give us secant squared u du. And then we'll make this substitution. So if our t value is infinity, then u must be pi over 2 here. And then if our t value is going to be 0, then our u value has to be 0. Then t again is tan squared of u, so we're going to have tan squared u to the z1 minus 1. And then here again, we're going to have 1 plus tan squared u. Then for dt here, we're going to have 2 tan u secant squared u du. Well, for 1 plus tan squared u, I'm going to use this identity that's equal to secant squared. So let's just write that in here. And then what I'm going to do is take this 2 and just bring it out front here. Now with exponent properties, I can just kind of cancel this one out and subtract 1 from here to combine it with this secant squared. For this tan squared, for this tan squared here, I'm going to use exponent properties and multiply the 2 out. So I'm going to write this as 2z1 minus 2 here. But if I multiply this by tan u, then we need to add 1 and get rid of that. But if we do that, this just becomes a minus 1. Okay, and then from here what I'm going to do is I'm just going to rewrite this in terms of sines and cosines, because it's a little confusing to deal with it the way it is here. So we're going to have, breaking up tan u as sine over cosine u, we're going to have sine to this exponent, 2z1 minus 1, over cosine 2z1 minus 1. And then secant squared, I'll bring it into the numerator as cosine squared, but what I'll do is I'll distribute the 2 in here, so we're going to have 2z1 plus 2 z2 and then a minus 2 here. Okay, but then what I can do is take this cosine and combine it with this cosine. And when I do that by exponent properties, the 2z1s are going to cancel, and then we're actually adding a 1 from this here. So when we put that all together, let's see what we have. We have 2 out front. We're going from 0 to pi over 2. We have sine 2z1 minus 1, and then we have cosine 2z2 minus 1, because we have minus 2 plus 1, so that's a minus 1 right there. Don't forget your u's, du. But the nice thing with that, this is actually our equation 3 right here. So by showing that the fourth integral is the same as the third integral, which is equal to the second integral, which is equal to this first integral, we've shown that these are all equal, and we can, for any of these, use this, go to our solution, and put it in terms of the gamma function. So I hope that was helpful. I thought it was interesting to kind of see how these all connect together. I know this could be a little confusing if you're not that familiar with it, but again, I'll provide a link to the full playlist, and you can check it out, some of the background. In some of the other videos, I go over the gamma function, how to calculate this, and I also have a whole bunch of examples in that playlist, so check that out. Thanks again for watching today. Please like and subscribe. Have a good day.